Hello, everyone. I'm Jamie Peterson, Director of WolframU. Last week, we launched version 15 of Wolfram Language and Mathematica, and today we start our new in version 15 webinar series. Today's session will be a fast-paced overview of the latest and greatest core functionality and new built-in AI features in the new version. We'll be returning each week for the next 4 weeks to bring you in-depth previews of core areas of Wolfram language. The next 3 sessions take place on Wednesdays, where we'll be covering time series, tabular, and model fitting on July 1st, visualization graphs, geography, and astronomy on July 8th, mathematical computation on the 15th, and on Thursday, July 23rd, we'll be talking about AI assistant and notebook technologies. If you've registered for the series from this page, then you're already registered for all the sessions and you'll receive email reminders prior to each webinar. You're also welcome to sign up for individual sessions from this page, depending on your interests. Today, I'm pleased to welcome John McClune as our first presenter. John is Director of Technical Communication and Strategy with Wolfram Research Europe, and he'll be sharing his version 15 overview with us today. You'll want to read Stephen Wolfram's release announcement for his comprehensive coverage of the new version and the release, and also his philosophy for applying computation in the world of AI. To try the examples from today's presentation, you'll want access to version 15, and we'll share a free trial offer that should be showing up on your screen now, so you can get started right away. Version 15 includes AI access, giving you access to AI Assistant. John will be talking more about the built-in AI Assistant in a few minutes, and we've put a link up on the screen where you can learn more as well. I'm going to ask a poll question to the webinar audience now about whether you've already upgraded to version 15. We have a YouTube live stream audience as well, and for those of you on YouTube, please feel free to type your responses, comments, and questions in the chat. We have Wolfram webinar and technical staff joining during the live stream to help us coordinate Q&A. So I encourage you to type your questions as we go along. Our staff will answer what we can in typed responses to you, and we'll save some questions for John to address at the end of his presentation. Let's take a look at that poll, how we're doing there. Thank you for answering the question. Perfect. That's a great mix, and glad to see so many have already gotten their access and their upgrade to version 15. Let me point out just a couple things in the webinar interface before I go. A download link with the webinar presentation notebook appears in the pinned note at the top of the chat panel. And that Q&A area is where you can submit questions as we go along and where you can read the published Q&A. Finally, make note of the full screen toggle available in the top right corner of the presentation window. We'll be making new notebooks available each week as we continue this series, and we hope you'll plan to join us at all the upcoming new in version 15 webinars. So thank you for your attention. Without any further delay, I'll pass things over to John McClune with our featured overview presentation.
Thank you very much, Jamie. So I guess this is getting to be a bit of a tradition for me to do a welcome to the new version of Mathematica. This time I've got a lot to say, so we'll get on straight away. And some of it, I'm afraid, is going to be a bit superficial because even with the hour and a quarter that we've got, I'm not going to be able to cover everything that is in this new release. It's so extensive. So I'm just going to share here my screen, and we'll get going. So as is my usual way of thinking about these things, I'm going to start with the features that kind of are kind of in your face and affect everyone. So we're going to start with things to do with the AI and interface changes, and then we're going to spend quite a lot of time talking about data and a little bit about visualization. There's some language things which matter to people like me, but perhaps a narrower for those of you who use Mathematica principally interactively. And then we're going to go through some specialist vertical domains, math, astronomy, biochemistry, and I'm going to introduce one new domain that is new to the Wolfram language entirely. So let's start with AI. As Jamie said, probably the headline thing here is that the Wolfram Assistant that we've had in Mathematica for at least a version now, we are making free to all users who have active subscriptions. That includes if you're accessing it through a site license or whether you have a personal subscription, but every active subscription gets the AI assistant included free of charge as of version 15. So if you are on 14.3 still, then upgrade now, and that will just automatically be enabled when you sign in. And that's a big, I think, game changer for, you know, what has always been historically the kind of the challenge of the Wolfram language is that we're a small language in terms of coverage compared to some of the big things like Java and Python and so on. And so we always have that getting started and learning the language. And the AI assistant kind of makes that go away because you can ask for the code you need and get it written in the notebook. Now, together with making it available to everyone, we also want to make it at your fingertips now that it's not a kind of side add-on feature. So there's some interface changes coming to make that easier and more available to you. So if I just switch to a kind of working notebook here. Okay, here we go. So here's a regular old notebook. I put in some random content. One fairly minor new feature, but significant for the AI, is there is now a docked footer that you can turn off if you don't like it and make it go away, but floats there and is always available for you to be able to ask chat questions straight into the notebook. Now, that in itself raises a couple of workflow questions of, do you want your chat to be part of the record? You know, notebooks are great at being able to record the calculations you've done, the inputs, the outputs, notes that you made for yourself. Do you want your conversation with the AI to be part of that? So if I do that within the doc cell at the bottom, and then let's do something trivial here, plot a wobbly line, then that's going to inject that conversation into the notebook at the current insertion, along with the answer of what it comes up with here. And it's hopefully going to come up with some suggested piece of code which I can execute into the notebook and run. The alternative is that you want this as something that doesn't pollute your work. And we've always had the Notebook Assist as a side window. What we're now doing is making that a little bit more convenient by having a sidebar that puts the chat out of the flow. So the chat occurs down the side. But now, as of version 15, that's docked to the window so that you don't get kind of muddled between layers of windows on top of each other, that the conversation there is attached, but it doesn't save with the notebook. It's an entirely side chat. So that's totally down to your preferred way of working. There is also a pro subscription which you can pay for, which gets you more advanced sort of cutting edge AI models. It's got the same capabilities in terms of accessing documentation and accessing execution tools, but it's just a more cutting edge model for the intelligence. And you can see here from the little tooltip that I'm on a pro subscription. So real game changer, I think, for those obscure bits of Mathematica where sometimes it's too, you know, the cognitive load of trying to remember what the function is and how to use it puts you off using it. And nobody knows the whole of Mathematica. So even for fairly advanced users, having the AI able just to write code for you on demand is really a big step forward in ease of use. And particularly if you're doing things like teaching with Mathematica, where you don't want to spend too much of your class time teaching Wolfram language before you start teaching the physics or biochemistry or whatever it is that you're using the Wolfram language as a vehicle to teach. So again, making it accessible instantly. Really nice for ease of use. Now, like most things we do in the Wolfram language, there is anything you can do that's user interface usually has a programmatic equivalent. And here there's been a little bit of difference that we're closing out, that the Wolfram Assistant was actually more capable than a persona that you could program yourself. And the reason was that the Wolfram Assistant could read the documentation on demand. So before it tried to plot that wobbly line, it probably looked up the documentation for plot and list plot so that it would be more likely to write accurate code. And we've now made that available so that if you're doing things with your own LLM code, so here I'm using LLM Synthesize, you can use the Wolfram AI Assistant as a chat evaluator, and that not only uses the AI that comes with your subscription, but it also injects in the documentation and other tooling that makes it better than out-of-the-box AI for writing Wolfram language code. Now, not strictly a part of Wolfram language, but I think it's like a relevant thing to point out here is that we are also expanding the tooling actually, I'm getting ahead of myself here. Sorry, still talking about users of the Wolfram language as the kind of primary environment. One of the things that we've also done is extend the tooling for external programming tools. So the notebooks are a great environment for experimentation. Whenever I try and play around with a piece of code and try and get it working, I'm always in a notebook. That kind of instant feedback and recording all of your kind of thoughts in a flow is really the best thing for exploration. When I'm writing large project code, I lead the consulting team here in Europe, and we're writing projects sometimes with 2 or 3 people on them that results in thousands of lines of code, then the notebook isn't the best environment. And there we start using things like my preferred is Visual Studio that I use to write my Wolfram language code. So we also now have some tooling for a range of these various competing developer environments that use AI separately. So in fact, I can show you if I go back here to my working notebook for a moment and go to Edit Preferences. There is now in the Services for AIs, there is a dialog here where I can include, if I'm using Copilot command line, I can configure that to be able to work with Wolfram language better. And so all of these major platforms like Claude Code and the like, and Visual Studio Code, those all have immediate configuration. And what that basically does is it makes the skills and tooling available, including a local MCP server, so that even if I'm not using Mathematica or the Wolfram language directly, I'm writing code in VS Code. When I ask the AI in that, if I'm using Copilot to write code, it can run Wolfram language code itself automatically. So it can do things like write unit tests, run them and see if the tests pass, edit the code, rerun the tests, and go around in a loop until it gets the code working. So all of those things that these companies that are focused on developer environments for coding, they now get the benefit of Wolfram language integration and execution by virtue of these plugin components that you can add to those environments. So whether you're a kind of light interactive user in a notebook or a serious developer using developer tools, AI front and center. So I was got to slightly prematurely. For people who are not principally interested in Wolfram language, we also have a set of various augmentation APIs that allow external developers to access our tech stack. So the API that does documentation search to improve the quality of code writing, that's available as an API, so it can be plugged into externally developed tools. And we have an LLM evaluator, Agent 1, which does a mixture of Wolfram language, Wolfram Alpha, and AI on a single endpoint. So when I ask for this, none of this was computed locally. That ran that computation as part of that AI endpoint. And there's also a shared free MCP server for more kind of casual. You want your AI agent just to be able to do maths. You can tell it where to get Wolfram calculations from. But these things are sort of outside of I'm assuming most of the audience here from the survey are already Wolfram language users, and so these things are really intended as developer tools for outside. But the first 4 very much putting AI at the center of your workflow. Okay, let's step away from AI and just talk about the interface. Just a few things here. The most important thing probably is there's been a lot of back-end re-engineering of notebooks, which makes them just faster and more scalable. So they open faster. Find, if I do Command F here and type, for example, let's take in the top right corner, you can see there's a little docked Find window I just opened. I'm going to type fast here, and instantly I can see that I've got 7 matches through this document, and 3 of them that are having to be on the screen have lit up in real time. So real-time search and replace is now just a core feature, whereas before, searching through a large notebook like this with lots of images in it might have taken 10, 15 seconds to find each of those things and to replace them. Now it's real-time search. And if I close that, those will unhighlight. We've extended the notion of storing information in the notebook to add in tabular. So we'll come back to tabular in a minute about data, but tabular is the new framework we built for column-oriented rectangular data science, and is very much intended to scale large. So while its kind of default mode for large data is outside storing outside of the notebook, there's now a little standardized icon where you can click on your tabular and say store in notebook, and then you can save the notebook, and all of the data in a reproducible way is stored within the tabular object. You might have a small rectangular display on screen that shows you the rows and columns that you can scroll through, but all of the data would then be embedded in there. So in the same way you can store video and audio in the notebook or not at your discretion, you can now do that with tabular. And there was one of the few places in the language.
Sorry to interrupt, John. I don't think you're sharing your screen. It just says notebooks. Faster, more.
Am I highlighting support for notebooks 2 GB? Did that light up?
Yes.
Okay, I wasn't actually showing anything special about tabular. It was just words this time.
Okay, and remember to hide the message at the bottom.
Oh yes, that come back again, has it? Okay, thank you.
Thank you.
Okay. Yeah, so there used to be a hard limit that notebooks couldn't be larger than 2 GB, and particularly once you can now store tabular objects within them, it's become important to get rid of that ceiling. So this re-engineering has allowed very large notebooks to be both possible and practical. Okay, another cosmetic feature this time is notebook themes. So we've for a long time had the ability to have different style sheets, and let's just switch over to this notebook that I had here. And so the fact that sections have a line across them and a certain font size, all of those things have been notebook set up. Themes are really a subset of that. If all you care about is the color sets that a notebook is in, then we can change that without having to change anything structural about the notebook. So if I just close this sidebar and open this information sidebar where I can switch between things like light and dark mode, you'll now see that there is a themes option that lets me switch between let's say I want something a bit kind of softly colored. I can switch to a garden theme and or natural and pastel, and you can see all the colors are switching, but the structural elements of the notebook remain the same. And like everything else, these things are controllable, so you can also use at a programmatic level this new capability theme color that allows me to decide whether or not I want a color to follow the theme or not. So here I've colored 2 discs red. One of them I've explicitly made red, and the other one I've said theme color accent 1. And if I switch between themes in this notebook, you see that the theme color follows in this theme color of the code. On this theme, they're not synchronized, but you can have them hard coded. So everything programmatic and point and click controlled. Now, something that's a bit more functional and practical is external evaluate cells now have environment information embedded. So what do I mean by that? Well, we've had for quite a long time the ability to have other language cells within a notebook. So I can have a cell where anything I type in here, I'm not going to run this here because I don't think I've configured Python on this machine, but I could evaluate something in a Python environment. Those cells now have this extra docked information at the top, which I can open and change to decide, is that cell using the same my default Python session, or do I want a separate Python session for this notebook, or a separate Python session that is configured in some special way for this notebook? So you can see in this particular Python cell, I've got it configured to expect NumPy, ZMQ, and PyArrow and TS data to be part of the configuration. And not only does that allow me to have multiple cells that are speaking to different environments, it also allows me to make sure that my environment is portable. So if I save this notebook and send it to you and you try and evaluate this cell, not only is it going to try and evaluate in Python on your machine, but it's going to configure a virtual environment that's got those dependencies built in. So even if you haven't installed NumPy, it should go away, fetch NumPy and set it up. And so this cell will just work. First time you might have a significant delay while it downloads and reinstalls these things. And second time it'll be cached for future use. And so this allows them, for example, in SQL cells, you might have one cell connected to one database, but another input cell connected to a different database. And so in the same notebook, you can be doing SQL queries directly in SQL alongside your Wolfram language code, but talking to multiple databases. Okay, notebooks have, obviously we invented notebooks way back in the day and still have the richest notebook environment out there, but others have cottoned onto the idea of notebooks as a kind of working metaphor. So there are other notebook sort of clones out there, from very light things like VS Code to slightly less light things like Jupyter. We now have import for those. So if you have a Jupyter notebook, you can just open it as a Wolfram notebook, and likewise import VS Code notebooks if you want to work in those environments. And then finally, last cosmetic feature, but kind of cute. You have this problem very often where you have to choose between the level of verbosity of outputs in a notebook. And up to now, we've had basically you can show it all, or you can compress it down, or you can make a very elided form, but nothing very display oriented that is elided. And so we now have this very display oriented elidation where I've got a large cell of input here, and I want to give you a hint of what it looks like, but you don't care about the full page of details that is the full output. And so we now have this torn cell style that I can set up that gives us kind of a metaphor for having ripped off the contents to show you that there's more, but we're not going to show it. In fact, this is programmatically, both programmatically and mouse controllable, so I can set the level of where the tear is, and all the information is actually in there, but it's compact display. Okay, notebooks mostly cosmetic. Let's go on to some things that are now functional. What we're really here for is computation. And I'm going to spend quite a while on data. Excuse me. And probably the headline thing here is some really significant reworking of time series and event series. So the core sort of headline driving force here is that time series have been this data construct that we have for time value pairs. So if you're making observations, you're measuring the temperature of something from a device, you're going to get a timestamp every time you look at the temperature and a value. And event series are the same thing, but are considered to be discrete things rather than time series are sort of samples from something that's notionally continuous, and event series are the same thing, but they're samples that are strictly discrete. But then it's sort of roughly the same thing. Now, it's been possible because of the symbolic nature of the Wolfram language to put things in time series that were not numbers, but it was never really designed with that in mind. And so a lot of things that you would do if you put something like an association in didn't really work, or they worked sometimes by coincidence. We've now re-engineered time series so that it's multi-valued by design. So here's a time series. I'm just going to load some data into memory here. And if I look up a value for what happened at that time series at a certain point in time, you can see here the nearest lookup that it found was this timestamp, but there were two observations made. There's a geo position and an elevation. So this is some kind of geo tracking device that is taking multiple observations each time it checks in. But of course, you have to worry about what happens if you only get one of those values, if some of them are missing. So time series deals with that, with proper handling of missings now throughout this multi-track setup. And really just much more flexible infrastructure for handling kind of multiple values, kind of columns within a time series. So with that comes a lot of joining up baggage. So one of those things is we've extended a lot of the visualizations to automatically take this idea of column-oriented notation that we've used in other functionality before. So now I can take that time series and say, I want to see a dateless plot, but only of the elevation column. Or I want to take the first 100 observations from the geo position and put those on a map. So all of these visualizations now extend to not having to do a two-step thing where you pull out the column you're interested in and then ask for a dateless plot. In a single step, I can take the time series and talk about one or more columns that I'm interested in a direct notation. So that's really just sort of syntax to make these things convenient. Another thing that with this revamping of the time series is that the time column in the old time series was strictly a number. It was always converted to a real number that was using absolute time as its reference. But of course, Wolfram language has powerful support for all kinds of date-related issues like different date calendar systems and date granularity. So now making dates work correctly within time series is part of this rework. So let me run two calculations here where I'm asking for that data at 5 o'clock on the 17th of September from whenever it was collected. And you can see here that I've got two different values back because there's a little bit of automation here about the interpretation of what I've asked for. In one, I said at exactly 5 o'clock to the second, or even to the fraction of a second. And the other one I've said at 5 o'clock. And the interpretation here is the granularity. This is assumed to be the hour of 5 o'clock. and this is assumed to be at that particular second. I can be much more explicit about that and say, let's put in the granularity being day, and get the whole day that 5 o'clock on the 17th of the 9th was involved in. And what it's doing is effectively taking it a weighted average across that time interval without me having to extract all of the data, figure out whether they were regularly sampled, because you can't just take an average of the numbers. You've got to check whether there were more samples at the beginning of the hour and then only one in the second half of the hour. So it has to take all of that into account in order to be able to do these date granular operations. And now it does that kind of magically out of the box when I ask for values on a granularity that is not instantaneous. There's a few new time series operations. There's a quick summary operation that will give you an overview of things like the mean, median, max histograms of the different columns. This, of course, is customizable, but with 0 arguments. Those are the columns that it will choose for you, but you can specify which columns you want. We can look for events that are happening in a time series. So time series events takes my time series and turns into an event series of when the events happened. And there's a fairly small set of events here. What I've asked here is for local maxima. So obviously we're on a walk here, and I want to find out when did we hit the top of some hills. And what does maxima mean? Well, it depends on the time interval. Do we mean the global maximum of the whole walk? No, we mean on a 10-minute interval. Find the points where I've never been higher in within 10 minutes of that moment. And it's found 5 different event series, and we can throw those onto a plot of the original elevation. You can see here the moments where I hit the high points on this walk. So we can find local maxima, local minima. We can find crossings. That's when the time series passes through a value, up crossings and down crossings. So you can say when does it cross 0 from negative to positive would be an up crossing, for example. And also another convenience function, event series accumulate, is kind of a running total of events within an event series. So here we're going from events back to time series, but with the cumulative value. And this now is a plot of the number of peaks that I've climbed cumulatively over the course of that walk. And of course, they go up in steps. Each time there's an event, it goes up in a discrete amount. So convenience functions that are doing typical time series operations sort of out of the box. Now, you might think that extending time series with all this extra date understanding and multi-column orientation would come at some computational cost. Actually, the opposite is true. That time series in Wolfram Language 15 is faster than it was in 14.3. In some cases, dramatically faster. And the reason is that time series, we've got time and value stamps. Well, these are rectangular data. We've got a column for time and a column for each of the values. That's the same thing as tabular. So now, behind the scenes, time series are tabular. All of this infrastructure that we built that uses the compiler accelerated native type recognition to then apply compiler accelerated functionality, knowing that the entire column is of the same type, that makes tabular really fast and also sometimes very space efficient in storage. That is now automatically applied to time series. The only difference is the interpretation, that some of the automation of what it means when you do arithmetic with a time series is different than when you do arithmetic with a tabular, but structurally they're the same thing. And in fact, we can switch programmatically back and forth between the two. So if I ask for the time series structure, you'll see here that that the types here are compiler accelerated types. So the timestamp is a date held as integer 64s behind the scenes. The quantity are real quantities and geopositions. When I say what's a tabular version of that, well, here is a tabular object now where the timestamp has just been converted into a column with the label timestamp. And if I take anything where there is a column called timestamp and I say do time series of that, it will automatically infer the time versus the other operations. If I don't have a column called timestamp, if I've got, if it's got a different name or I've got multiple times, then to go back from tabular to time series, I have to tell it which column is the canonical time column for the time series. But other than that, it's entirely automatically interchangeable. So really big change to a function that's been around for quite a while to make the thing a kind of much better without you having to change any of your code. But there is some new functionality that you can do that will, if you're doing further development time series, is going to be much more elegant. But this should run unchanged for your existing code. It should be 100% backward compatible, but the fact that it's been rewritten effectively entirely behind the scenes. It has some real kind of performance improvements. And just to support that, many of the data formats, particularly things like column-oriented formats, are directly importable into time series. You don't have to go through a multiple step of importing the thing and then saying make that a time series. You can, if you know you want to treat it as a time series, you can bring data in from files in a single step directly as one of these optimized time series. So all built on top of Tabular. Tabular is relatively new, so there is still work going on in Tabular, and we've got a bunch of things to add that make Tabular itself fundamentally better. One of those is just on the import side. It's really, it's sort of, in terms of functionality, it's quite cosmetic that you can describe which columns you want to bring in. But actually, for big data science, it really is important for pushing back the barriers. So I haven't got this on this machine, so this is timings I ran on my MacBook Pro back at my desk. So I've got a M3 MacBook Pro, 3-year-old one, and I had this Kaggle data set that I fetched, which was about 2 gigabytes in size. So a modest, decent sized data set. And I can import that in as a tabular, and it took 8 seconds and takes slightly less memory than it did on disk from the CSV file to have that in as a tabular. With this new syntax, rather than having to bring in the entire data set, which I think has something like 15 columns in it, it might be that all I'm interested in are the columns for distance and the tip amount. So I can pull those in directly and we get the data in a bit faster. But here's the big difference, is that I only have to use up 200 megabytes of memory. Before, first of all, I had to waste an extra 2 seconds importing the data, but the main problem was I'd have to import 2 gigabytes of data before throwing away about 1.6 gigabytes of data by discarding the columns I'm not interested in. Now, 2 gigabytes isn't that big. On a MacBook Pro, I've got, I don't know what I've got, 32 gigabytes of RAM. This is pretty easy to bring in that data set in. But if we were talking about a 60 gigabyte data set, well, I can no longer bring that into memory on my laptop. But I could potentially bring in the columns I'm interested in into memory and still have it fit. So it's, in terms of how far you can go in terms of big data before you start having to jump through hoops to juggle the data you're dealing with, that's now been pushed back further. And of course, because we're supporting direct import for various, there are more optimized formats. So CSV isn't actually very good for column-oriented data because you have to touch every row in order to then take the 2 columns out that you're interested in. There are formats that are actually much more modern and optimized. And so if I had the thing originally in Parquet format, then I can bring the thing in much, much faster, although with the same amount of final memory footprint. Okay, so the next big thing in data, which we're at the sort of the first steps of a journey that we'll see more of in future versions, is a new model fitting framework. And I really like this because this model fitting framework sort of exemplifies everything about when Wolfram language is at its best. And when people ask me what makes Wolfram language different than cobbling together some libraries in Python or R and trying to do the same thing, and I always tell people that it comes down to 3 things: all-in-one, automation, and integration. All in one, everything is there. You don't have to hunt around for libraries and figure out whether it's a reliable library from a good source. Everything that you might need is at your fingertips from the moment of installation. And so, as you would expect, this is a built-in function. But oops, I opened the wrong section. But let me go into it in a bit more detail before I explain how automation and the integration is implemented here. So at first glance, this is syntactic sugar. We've had for a long time the ability to fit data. So here's some data that I've just generated randomly. It could be from some experiment, and I can fit a polynomial with linear model fit. We've had this function for many years. And in fact, fit, which was its predecessor, right back to version 1 of Mathematica 30 years ago. And I'm describing here a basis set of a polynomial up to a quadratic, and it puts those terms together to make my fit. Here's the new function, model fit data polynomial model 2. And that's the polynomial model 2 is saying the same thing. I want a quadratic fit model, and we get something back, which is a polynomial model. So we can see you get the same numbers. It's the same functionality. It's fit slightly more elegantly into our plotting function. So I could do things like list plots with plot bits of that model without having to specify the range I'm plotting over. That can be automated, but otherwise it's just kind of a new syntax. So where is it different? Why are we doing this? Oops. Well, the first thing is automatic model selection, something that we've never had in the Wolfram language, is now brought to bear across that model space. So where I said polynomial model 2, well, that 2 is a specific polynomial model, but I could be much more general and say I want a polynomial model. It could be quadratic, it could be order 10, it could be an order 200 polynomial, and probably massive overfit. So you get this trade-off of we'll get a better fit the bigger the polynomial model we use in terms of minimizing the sum of the errors, but at a cost of a more complicated model that's more likely to overfit. And so there's this trade-off of trying to find when are we getting a better model description for an acceptable cost in model complexity. And that's the model selection problem. What is the best model that is flexible enough but not too flexible? And that is now automated without me having to do anything extra. I just underspecify the input by saying I just want a polynomial model, and it's decided that it's going to go to a order 3 model, but no higher. And that parameter space, I can give it as an exact number if I know what I want. I can give it totally open-ended, or I can give it constrained. So I could say, for example, I want to fit that with up to quadratic. And so it's decided actually you do need quadratic. A straight line is a terrible fit. So out of its choice of polynomial of order 0, 1, or 2, it's settled on 2. I could be a bit crazier and say I want an even model. I want something between 2 and order 10 polynomial, but it can only go up in steps of 2. So I don't want any odd leading terms. And you can see here it's picked an order 10 polynomial as now being under that constraint the best fit. So there's additional options I can specify here for how it picks those that model, but out of the box here we've now got automatic model selection, which in as sort of simple a way as you can imagine. So that's the sort of automation of the Wolfram language that we're trying to make it so that if you don't specify things, we can figure out what the right parameter is to put in there, or the right algorithm to use, or the kinds of automation that we put in all over the place whenever you see automatic as an option within the options of the Wolfram language. The integration, though, it comes from the idea that linear model fitting gives us a linear combination of some base set, but that's just one kind of model. There are other kinds of model out there. There's periodic models, which you can do by linear combination, but you can also do by nonlinear models. And there's machine learning models. So what we want to do is to unify all of those things under the concept of sort of a regression fitting type task. So the model, oh, I'm getting ahead of myself again here, but let's do that right now. Under model types, there's actually all kinds of models I could choose from. I could use a k-nearest neighbor sort of classic machine learning model. And again, I'm giving it some kind of up to specification, say pick up to 10 neighbors. It's decided 10 neighbors was best. And everything that I've written elsewhere just works. So just being able to say, plot that model against data. I could use a perceptron neural net. And here it's decided I didn't specify how deep, but it's decided 2 perceptrons is enough. And these things join up with the rest of the framework. So if I ask for the actual neural net here, what I'm getting is a net chain model, exactly what our neural net framework has provided you for. And you've got some net chain here that you could examine the weights and biases on, or you could retrain with some different data, or do some kind of model fit analysis using net measurements, even turn the thing into a kind of schematic graphic. So the neural net framework integrates in other kind of things that used to be the preserve of classify or predict. Well, I guess predict in this case, fit in, all elegantly unified under model fit. So one function that unifies all these different areas. And some of these things even fit in with things like programming. So if I ask for a decision tree model, I'm going to force the level 3 because I think it naturally wants to go a bit deeper on this. Then that fits in with our graph theory representation. So here's the graph, the tree representation of that decision tree model that says our best decision tree is to pivot on whether or not the number is above or below 8. And if it is, then we next look at some the other value, whether it's less than, sorry, if it's below, then next we're asking, is it less than or equal to 1.5, and so on. Well, I could turn that into a code expression and then drop that straight into code and represent the thing as if then else statements with a nested piece of code. So everything is really joining up. That's programming, machine learning, neural nets, fitting, all join up with this idea of model and selection. You can write a whole piece of code that's got some kind of model selection at its core, and then think, oh, what if I rerun that? And instead of doing linear regression, we did, we did some kind of periodic model. You don't have to rewrite code all over the place because the things are fundamentally different. You could just swap out the model choice parameter and get something completely, automatically ripple through your calculations. Now, I mentioned in passing that how we select the model is we've automated that entirely, but like most of these things, that's the default is to make choices for you in a very automated way, but we expose all of that to you. So there are an absolute ton of things that we can measure about the quality of the fit. So here's the headline report on that, of the degree that we chose, the R-squared value bias, and somewhere down here there's a little visualization of the models it considered and what their various losses and errors were, to analyze, see how it came about its decision. And if we really care about those, there's an absolute ton of these properties of different ways of measuring the goodness of fit or the information density of the model that we can query. And let's pull out one of those. So here is the cross-validation chart for the 5 different orders of polynomial that it considered against the distribution of the errors that you get. So all of these different measures, you could put those in at the model selection level and say, at the point where it is that I did this, I said, I did it back here. When I did pick a polynomial model, I can add in here optionally using a model selection criteria that goes to some function of those different criteria. So I can spell out exactly how I want it to decide which is the best model if I care, if I either have a deep understanding of it and the data, or because I really want to be able to have explainability of exactly what went on within my code. So quite a lot there, all wrapped up in essentially a single command. Have I covered everything? I have. Right, let's move on. So still in data, I'll skip over the next one. The neural network backend that powers net model, we now have alternatives. It's the start of a process of making the net execution and training model just another one of those optional algorithmic details. At the moment, where I think we have just a choice of 2 backends, but we'll be extending that further over future versions so that you can benefit from some backends are sometimes faster or slower for different hardware configurations or different models, and it gives you the choice to switch backends. Got a little bit more to say on ordinal and nominal data, something that symbolic representation has given us as a side effect for a long time, but we're now making these things sort of first-class objects, initially giving us a little bit of automation, but will have more importance for high-level automation in future versions. And these are ordinal and nominal data. So these are things where our data has names, not values. Now, of course, we could just use strings, and for ordinal value, for nominal value, that sort of amounts to the same thing. But for ordinal, it's different. So with ordinal data, we're taking some possible labels, but we are saying that they are ordered. So tiny is smaller than small, and medium is bigger than small. And in the context of that, we have this data object called huge. Now, in practice, we don't want to spell that out every time we have a value. So there's an operator form where I can set up my type by saying it's ordinal with this range of values, and then I can apply that type to the value in future. So this amounts to the same thing. But here we're saying small in the context of this data type. And now that idea feeds a whole bunch of different bits of the computational system automatically. So for example, if I ask for random choices, I can generate some data out of that type, randomly selecting from them. If I do a categorical histogram here, you'll notice it, even though it didn't have any huges in the data set, it left space for it because it knows that this value can encompass the value huge. And if I do one where, I'm trying to get one where there's a gap in the middle. Yeah, so here's one where there's 2 of them weren't mentioned. Even though they weren't mentioned, it makes space for them in histogram, and it orders the histogram appropriately. Let's make this a bit bigger. Let's have more data here. Let's have 50 of these. When we do things like list plot, again, we can have scaling functions that automatically understand that they should treat these things as numbers, but ordered appropriately so that the tiny ones are at the bottom and the huge ones are at the top. We can select by ordinal values. So here I'm selecting everything from that data that is at least big. So we get the big and the huge values, but we don't get the small and tiny, and things like sorting work out of the box. So now these labels are no longer just strings that have no meaning until you do something to substitute values in for them later. They understand all of their ordering capabilities automatically. And we're going to make use of that within things like data set and so on in order to have accelerated ordinal and nominal data in future. So this is while of modest value now. If you're doing this kind of stuff, I encourage you to embrace the type because we'll make better use of it in future upgrades. There's a few new import formats and upgrades to existing formats. You can download this notebook after the webinar and view these things on your own. Perhaps slightly bigger is the data connection object that allows us to point to external data sources in a much richer way than just a URL. Now is extended to some data lake frameworks, so Databricks and Snowflake. We can reach into a data warehouse that's, in this case, a Databricks warehouse with sufficient information that represents a particular query and get a data object that we can now import against. So it's a symbolic representation of automatic connectivity, which, as you move into kind of bigger corporate data sets, then a lot of this data is stored in these kinds of data lake frameworks. Okay. That's quite a lot on data. How are we doing on time? We need to press on quickly. Visualization, I'm going to largely skim over because we've seen some of that already. Direct plotting of time series components. We've seen model fitting, being able to throw fits directly onto plots has been extended with this whole new model fitting framework. There's some new statistical visualizations. So we've had distribution chart for a while, but there's two new chart types within distribution charts. So there's a kind of smooth histogram for multiple data sets, and there is a discrete histogram laid out sort of horizontally on this across the data sets, so you can show side-by-side data sets. The kind of thing you would normally, a lot of people would use things like box whisker charts for. These are just two new ways of showing that same kind of data, side-by-side distributions. There is perhaps more general a multi-panel visualization. So it's been easy with graphics grid to make multiple panel visualizations where we have a single graphic here that resizes collectively with multiple plots inside it. But it's had some serious limitations. So it treats each graphic in its own right. I mean, that's sometimes what you want. Don't mess with my graphic. Just stick it in a grid so that things lay out neatly next to each other. But you'll notice here that if we're really comparing these things, that this first plot is plotted for up to 0.6. And the second one is plotted up to 0.4 because they've all got automatic scaling. So these two curves look identical because they've rescaled to fill the maximum space. What plot grid does is it factors out all the axes on the same row, and it factors out vertically the axes on the same column so that they are shown once and shared. So now we've got all the plots go up to 0.6, and this plot has shrunk slightly, not using its whole vertical space, so that it comes to the slightly above 0.4 that it was in the original. And you can take that further and force all of the horizontal and vertical to share exactly the same axes. So now in this one, each row is independently choosing its vertical y-axis, but in this one, all the y-axes are the same and all the x-axes are the same. And this also works for labeling. So you can factor out labels and have common labels for the columns and common labels for the rows. So it's much easier to make publication quality side-by-side graphics where you are doing like-for-like comparisons as you look across the graphic rather than side-by-side with their own worldview, their own coordinate system. There's some new graph visualizations, so you can color and size vertices and edges on graphs now as an automatic display. Those things can be fed directly by computed values. So here, rather than having to generate the values and feed them back in, if I want to see the betweenness centrality on that graph, I just have to say plot that property across the graph. And now this has very high betweenness centrality and this vertex doesn't. Or you can pass them in as specific values. Same with edges. We can feed in edge capacities now or edge weights and have the thickness of and the darkness of the opacity or color of the edge computed, or I can give a property and just show that property of the graph as a thickness and brightness. So just, nice direct visualizations of graphs beyond just the connectivity, which we focused on in the past. Right, a little bit of explanation needed on geo-axes. We've been able to put axes on geoplots for a long time. Here is a plot of the Wolfram Research Europe office. We sit in this little corner over here, where I'm sat right now in England. And on a local level, just having axes turned on is perfectly valid. So here we're seeing the latitude and longitude of where I am in the UK, and there's nothing wrong with this at all. The problem with using axes is the axes are in the coordinate system of the rectangle on screen, which is fine at a local scale. But as you zoom out, this is not an accurate representation of a line across the United Kingdom, because the latitude over here is not the same as the latitude here on the line, because we've got map projections to take into account. And that's what the new geo-axis does. We can use geo-axes to put an axis on, and likewise with grid lines, we can specify specific grid lines or automatic grid lines, axes centered somewhere, or automatically centered according to what we're looking at, but they respect the projection, so they curve appropriately and they converge appropriately. And this is handled across all scales. So at some point, those lines become circles when we're in a, I'm not sure what our default projection here, probably Mercator, not sure, or orthographic. But these things aren't even just kind of straight circles and curves. If you go into weirder projections, they can be all kinds of incredible shapes, and that works across any projection for any choice of grid lines and axes that we support. And here's one where it's going truly great all over the place. So proper axes and grids on geographics at all scales. The next one's pure syntactic sugar, but it's really quite elegant, is that when you are coloring things, there is this new sort of association syntax where elements in groups can have coloring information attached to each element or each group separately, and then they compose to combine. And you could do these things before, but you ended up having to have a very complicated syntax to specify how to color and scale points across a multivariate data set. And now there's this, a nice tight notation for that. Okay, let's go on to the programming language. Core to everything, but depending on how deeply you get involved in programming, these will be of different interest to you. The first is quite a simple thing. We introduced a couple of versions ago within the compiler was an incremental object, and that has proved useful enough that we've extended it to the core language. And the idea of incremental objects is you set up an object, but every time we ask for the object, it changes its value. So the very simplest one is something that goes through a range of numbers. So when we ask for next value, we get a number. But if I ask for the next value on the object again, I get the next number and the next one. So you could set this up yourself by setting up a global variable, kind of dangerous. So you might want to scope the whole thing in something to keep it localized. But then you would have to do increments on that object. And if you're doing this multiple times, you need to make sure that the variable that you're storing in is changed if you have multiple objects going on at once. But not very difficult to do. But where it gets interesting is there are other kinds of incremental objects. So this one is a permutations object. And now when I ask for this, I get the permutations of, in this case, I ask for the numbers 1 through to 20. So there's the first permutation. When I ask for the next permutation, you can see it's gone on to 17, 18, 20, 19. And tracking this through over time, obviously, is a challenging thing to do. You'd have to write non-trivial code to be able to figure out what the next permutation is. You could enumerate all of them with permutations, but that's not practical when you're up to things like 20 permutations, because I think we end up with this number of permutations. And if I'm going to enumerate every one of those, we're going to use up a few $1 million worth of RAM just to hold that object that we're going to map over. So it's very convenient sometimes to be able to march through these things only one at a time and just worry about the current one that we're on, test it for whatever we're investigating, and then move on to the next one. And these things can be composed in order to make complex incremental object types. So here I'm doing something that ranges through integers, but folds in the next prime number and gives me an incremental object that goes through primes automatically. So very small, convenient thing for search type code that you're writing. The next one is much more zoomed out. The next one is very much a global thing. I'm not going to show the example here. I don't think we've got time to go into it, but let me tell you the key features. This is a modern replacement for the structure of begin package, begin, end, and end package that we've had since the first version of Mathematica. The challenge here, which you don't tend to have to worry about when you're writing small-scale code, is if I'm going to write a reusable package, then I'm going to have all kinds of symbols in it, some of which are internal functions in my package that only I care about, some of which are the functions I'm trying to write for you to be able to use. And somebody else is going to write a package that that you might load at the same time. So I have to worry about whether I've called my function and somebody else has called it function. And now what happens if you load both packages at once? And I want you to be able to see all of the functions I've written for you, but not get a big list of internal things that were written for my convenience. And that's what the begin package and begin structure dealt with. The limitations, though, of that were that you got pretty much an all or nothing type setup, and you had to kind of spell out everything that you were going to include. If you had writing a package that needs another package, you end up having to spell out all of the dependencies. So what the new structure does is makes it much easier just to say, load all of the files that are in this directory as being part of the same package. Declare things as being scoped to the package, scoped to the just to the single file that I'm currently working in, or exported globally. So now, rather than having to set all that stuff up front, which was the kind of convention in the old package where you would say at the top of the package, here's all the export symbols and then everything else is private, you can put that anywhere in the code. So you can make it very clear alongside the code, is this exported or not exported for exposure to other people? And then when you include packages, you don't have to take all of the functions that come in the package. You can say, import only this one function from this package that provides 20 functions to the user. So you don't have to worry about, I've accidentally loaded 20 commands I didn't realize I'd loaded because it was a big complicated package. I can just say, just load this one function from this package, or these 3 functions. So much more control. So both for certain types of operations, much more convenient to be able to say less in boilerplate code. But for more complex situations, easier to take control of, so you don't end up getting muddled about what is or isn't in context at any given time. So very much a modernization of existing functionality. The next one is all about large-scale code again, and we're trying to build in more modern error handling things that allow you to write production quality code. That when things go wrong, things always go wrong in code, either because you've made a mistake in your code, or the specification was wrong, or we've got a bug in our code. How do you handle those errors? And a couple of versions ago, we added enclose confirm framework, which was a really good way of having errors ripple upwards. That when something went wrong in a function, you can immediately exit and pass that error up, and you can check that anything you're using has had an error. What the throw exception and catch exception framework for allows you to do that without having to follow the errors all the way through the system. So here I've got a piece of code that that I've forced some exception condition in that says this is not intended to work for big numbers. Anything over 69, we're going to call an overflow. Obviously, it's not true in Wolfram language. You can do factorial for very big numbers. And then I've got a function that uses that, but I've not thought to check for errors here. So this code hasn't been written particularly well. I really ought to do something like enclose confirm wrapped around fac, so that if something goes wrong, I can pass it up. But I haven't. But later on, I'm using a function that uses that function. And here I want to say, well, if something went wrong, I want to catch that. So now when I do this calculation, it works. But when I do that calculation, this F catches a failure from deep down within the system. And with this framework comes the whole notion of types of failures, so that I might have a whole bunch of different kind of computation failures, of which an overflow is one. I might have a bunch of import-export failures. And so I might want to catch a specific overflow. And if later on, I might just say catch any computation. And if I missed the overflow, I'll catch it. But if I caught it when I was expecting an overflow, it will have already been dealt with. And then at the top level, I might say catch anything of any type of error. And then anything that I haven't handled more deeply down eventually catches all. So you've got this sort of bulletproof chance of catching errors where you expect them, and then handling them in a much more generic way where you never thought they would happen, even right up to the surface. So really kind of guaranteed error handling at some level, rather than cascading through the code causing mayhem along the way. I'm not going to go into this detail here. There's a bunch of improvements to the compiler. So these are functions that now are newly compilable or handle different data types or faster than compiler. The compiler is all about being able to take Wolfram language code, make upfront assumptions about data types, and make machine code executable fast versions of those functions by converting them into low-level virtual machine representation and then making a compiler that is for your specific hardware to be fast execution. So ongoing journey that we've been on for some years. Every version's got new compiler enhancements for real fast execution of particularly low-level code. Different kind of scaling problem. Wolfram Compute Services has a new feature. So these aren't new functions, remote batch submit and remote batch map submit. But there's new options to control them. But the main thing that's really exciting is that they work completely out of the box now. So without any configuration, if I've just installed and signed into Mathematica and I do this remote batch submit, I'm taking this piece of code here and I'm saying I want to run that on I want to set up an Amazon server that has Wolfram language on it, place this job on the server and run it. And when you're finished, shut down the server and destroy the server. And I've just done that. Zero configuration. My Wolfram login is enough to set that up through my credentials. And there is a geo zone for Europeans who have to run things in Europe. There is an option set. I want to run this computation in Europe. There is a machine type, so I can say here I'm just going to pick some sensible small machine, but I might say I want to run this thing on a 72 CPU machine with GPUs and a terabyte of RAM. And if I'm willing to pay for it, it'll provision that machine for me. I can control the cost with things like credit constraints, so I can say don't spend more than a certain amount. And once it's deployed here, we can see here my job hasn't started yet. It'll usually start within a few minutes, but it's been queued up. And at some point when this says completed, then I can use job evaluation result to get the value back. So it's a drop on the server, come back later when you got the answer. But being able to do that without any configuration, this is all built back against service credits in your Wolfram ID. So if you're part of a site license, you may have service credits provided for you by your administrator. Otherwise, this is something that you will have to have a subscription to, because I think the default single user license comes with 0 service credits, but you can top those up and it builds against those and refuses to do the computation if you're out of credits. It is not backed with a blank check credit card. It is you pre-purchase credits on it. Okay, so those are some things in the language design. How are we doing here? Yeah, so we're going to finish on quarter past, like I hoped, I think, because I'm going to skim this over quite quickly here as a domain of mathematics. I'll talk about a couple of these things. I'll talk about algebra very briefly. We introduced in 14.3 non-commutative algebra. So this is algebras where x times y is not necessarily the same thing as y times x. And we've added non-commutative algebra with relations, with conditions on it. So there's a general way to set this up where I can say what the generators are, but what the relationships are that about how these things do commute. And having set that algebra up, I can then do something like expand this piece of algebraic operation based on those rules. What's probably more useful is that 3 of these algebras have been set up out of the box. So Clifford algebra, Grassmann, and Weil algebras are all now predefined. So I can take some expression and do a non-commutative expand on that, say treating these x's and dx's as elements of a Weil algebra arrangement. So these things are algebras which have been well studied in things like geometric algebra, so unifying things like electromagnetism and quantum mechanics, or some of these algebras also used in things like visualizations or engineering things like stress and strain and fluid flux type calculations. So there are certain things that you can express very elegantly within these algebras, and now they're out of the box. If you know what they are, you'll hopefully be excited. If you don't, you probably can skip over this item. In the matrix space, we are filling out the space of this huge zoo of matrix operations. So there are a whole bunch of new ways of decomposing or reducing matrices, or improvements to existing matrix decompositions. There's a few new matrix operations. And again, I'm just going to leave this as a big collection of new matrix operations that are now available. I'm not going to go into the examples on those. they're all ways of changing a matrix into a shape where certain kinds of computations suddenly become much more efficient or much more compact. Similarly, special functions have, for a long time, well, probably forever, since the beginning of Mathematica, we have been the world leader in implementation of mathematical and physics special functions, so much so that at this point we've basically run out of special functions to cover, but we haven't run out of cases to cover. So some of the existing special functions like zeta, polylog, and harmonic number are now getting their multivariate generalizations supported, and likewise some new harmonic numbers, which I think are a new special function. And when we say we support special functions, that usually means throughout the system. So that means that when they pop up in the solutions to differential equations, they will just now appear in the solution. When you want to evaluate numerically, they'll evaluate for complex numbers or high precision numbers. So here's sort of high precision complex evaluations of that harmonic polylog. So full support for those special functions. There's a little bit more in calculus. dsolve has got mainly faster, but there's a little bit more capability and some new things in sum and integrate, mainly as a consequence of the new special functions. Some new things in PD modeling, which I think I have time to talk about at least one of these. So new algorithms behind the scenes, and we can specify PDs with spherical coordinates, fairly straightforward things. The derived quantities needs a bit more explanation. So within things like fluid dynamics, electromagnetics, and solid mechanics, there are PDs that we can solve, that we can describe fluid type problems and solve the PDE. But then having solved the PDE, working out some of these other properties is a computation on top of the solution to the PDE. So that's what things like fluid viscosity are, is a sort of downstream computation for the initial differential equation solution. So here's the dsolve. I'm taking a fluid flow component with some boundary conditions. In this case, it's fluid going in from a thin pipe into a fat pipe, and a stream plot of the solution. So the solution we get has three components: the x, y flow coordinates. So plotting those two together, we get a flow and a pressure value. And those are the 3 bits of the solution. Now, from the pressure and the flow, we can compute the fluid viscosity and the fluid viscous stress. And that's now a single step operation where we can take the variables and parameters of our problem and the result that we generated and get those 2 computed properties out. So that's basically what these things are doing, is giving you these real world physical properties in a very single step operation from the interpolating polynomials that dsolve spits out in these kind of very engineering physics real world type PD modeling situations. And one last, which I put into maths, it's really infrastructure, but it's again really related to linear algebra, is the data structure that we introduced in, I think, 14.2 or 14.3, GPU array, continues to get developed further. So a whole set of new operations now can automatically do optimized GPU calculations on these GPU arrays. This is an entirely performance related thing. The idea is we've got the standard data type. I'm making a matrix of 3000 by 3000 real numbers and asking for the eigenvalues pretty fast in core memory. But if I wrap that in GPU array, I'm telling it that this is now an object that where possible we want to operate on the GPU. And now when I ask for the eigenvalues, you see we're getting, I can't work that out, as 400 times faster. Looks like 400 times faster. These timings were from my, I don't sadly have a GPU on this broadcast computer, but these timings were from my MacBook Pro. So just standard laptop timings. And there's various other things that are now starting to use, where possible, mixed CPU and GPU operations in the graph computation space, and also in linear algebra type operations. And we also, in our external evaluate, if you do want to get down in the nuts and bolts, you can now write CUDA code more easily and to run that directly if you're really into the details of GPU operations. Okay, let's go into things that really are now specific domains in the last 5 or 10 minutes that I've got. I picked out 4 domains here. There's some things going on in astronomy. We have new orbital calculations. So the idea is that for an astronomical object, here we go. I've asked here for orbital elements of the moon, and we get various properties that come out. But this isn't static data because the orbital properties change for astronomical objects over time. So this is valid for when I ran this. I guess I wrote this talk on the 26th of May. And if I ask for the orbital elements in 1,000 years' time, the moon will have drifted further away. So it's different. And this works across all the astronomical objects in our astronomical database, so pretty broad. So, for example, here I'm asking for, I'm doing a computation based on the orbital elements of Halley's Comet and the Earth going around the Sun to see the relative, where Halley's Comet comes inside the Earth's orbit when it appears back on its next visit. And here I've got a little visualization when this loads in a second of the GPS satellite orbits, as was computed when I ran this piece of code last month. We also have some new support for computing with eclipses, so we can find eclipses. We can compute all kinds of properties of eclipses. So there's an eclipse coming up very shortly, but sadly in Europe it's going to be very low on the horizon, so I'm not going to bother going down to Spain for that one or up to Iceland. But this is the next eclipse after that, which is coming up in August 27. And this is where I'm going to go and see it in Tunisia, so I can make sure that I'm well within the path of totality with this envelope polygon calculation from the eclipse. And the geovisualizations that I've already shown you, things like geoaxes, they work on astronomical bodies too. So these things like geoaxes and grid lines are now also supported, not just on the Earth, but on other planets too. There's some things in chemistry. We've had the notion of substructures already, but now we have a substructure searching capability. So I can take some molecule and say I want to find any patterns of things that look like benzene rings within this molecule, and it can identify those automatically and give me the targeted substructure. There's one new light visualization. We've got a periodic table plot has now been elevated into the core language. And there's some new services for fetching protein data directly in language and some new properties on molecules. I haven't got time to go into those because I want to spend a couple of minutes on some system modeling and crossover things to our Wolfram system modeler and Modelica system modeling world. So we have this whole framework with system modeler that runs Modelica models, which are designed for large-scale simulations. So when you've got complex feedback loops, like that you are modeling the entire flow of a chemical plant or all of the electricity around the control system for a car, for example. And we've got two new capabilities that bring that world into the Wolfram language world in a rich way. So if you're building high fidelity models, you want all of those components of resistors and capacitors and pumps and heat sinks, and you want to just drop them onto a diagram and hierarchically design that visually, system model is what you want. Once you've built the model, analyzing it beyond specific simulations, that's where the Wolfram language is useful. And the two new ideas are system model surrogates and control system design in reinforcement learning. And whoops. Let me just open that section up. That's not looking very happy here. Oh, there we go. Oh, my camera died for some reason. That's why my machine wasn't happy. Are you still hearing me? Can somebody on...
Yes, John, we can still hear you.
Okay, you don't need to see my face. I'll just carry on. Right, so here we've got a fairly simple system model. It's a motor, it's got some mechanical components, an electrical one, and we can simulate it as we've always been able to in Wolfram language. So we take that model imported from system model or some other Modelica environment, and for some resistor, I simulated how the electrical, the inertia actually of this model will behave over time. Now, that's high fidelity modeling, very accurate, very useful, but relatively slow in a complex setup. This is pretty simple, but if you've got entire vehicle dynamics, that could take quite a long time to compute. The idea of system model surrogate train is use that model to generate all kinds of training values in some kind of parameter space that we think is plausible, generate training data and build a neural network model that then is going to try and emulate the high fidelity model. And here we can see the plot of the train version that is, at least to our kind of looking at with the naked eye, appears to do the same thing. So the benefit here is that once we've captured that in a neural net, it's much, much faster. And then we can also do other things like invert the neural net to make control systems or other kinds of sensitivity analysis and the like. But the main thing is being able to take these high fidelity, high quality models and generate a fast approximator of those models out of the box. In fact, we did at in our European tech services team, we did an entire project centered around doing this for an electric vehicle in order to be able to figure out which parts of the vehicle design were significant and which could be dispensed with to save money, and to simulate, to generate an attempt at a control system to manage the battery temperatures and the power flows to minimize energy use. And that's now sort of the guts of that project are wrapped up in this single automated function. The other is not dissimilar, but a slightly different purpose. So here's my example. I'm loading a library that happens to be some DLL on my machine. That's not important. The point is that it's a black box example. I don't know what this library does. And it could be a library, or it could even be a connection to something physical in the real world, where when I set parameters, something's cogs whir and machines move and something happens. All we know is that when we poke it, we get values back. And our job is to make a control system to keep this thing under control. So, you know, the canonical example here is if you wanted to make an autopilot for an aeroplane, you want it to fly level and straight. That's the keeping it under control. And if you were really reckless, you would put this on an aeroplane that doesn't know how to control the airplane and just say, go figure it out. And every time the thing went into a dive, it would try different controls to see which things fixed it and which didn't. And gradually, if it didn't crash every time, it would eventually learn how to fly the plane. And that's exactly what this LQ regulator train does, is it takes this black box library and it plays with it and learns how to control it. So it tries all kinds of ways of poking the thing to get it back under control. And then having trained on it in a reinforcement learning way, we end up with a system model controller. And now I can use that. And when I put it into this model in its desirable state on 0, I set it off with the value at 1. It poked it fairly quickly and got it down to 0. And then it wobbled a little bit, but it kept it under control. And here's the error plotted over time. So learning by doing in control system design. And again, basically automated out of the box. Right, our last domain, and before I wrap, I'm just a little bit over time here, is not core to our purpose at Wolfram Language, but actually is a good exemplar of how the computational paradigm really can be brought to bear in all kinds of interesting directions. And I know that a lot of our users actually are kind of musical in their pastime. There may be one or two of you out there who actually do computational analysis of music for a living, and in which case these are kind of interesting functionality. But as a kind of whimsical see also, the idea here is that we have now a full representation of music, so not just kind of symbolic notes, but the whole score. And those things are now computable with a set of, at the moment, fairly basic operations. So there is a visualization that will take that, actually, I guess we saw it automatically in the play object that came back. We can analyze that object for things like what kind of pitch class the different notes are in. We could estimate what key it's being placed in. It seems like it's been set to be in C minor. And I can transform it and move it up and semitones to make a newly pitched version that is still mathematically valid, and estimate the key from that. We can see it's now estimated to be in G minor. So just kind of computational operations. But I think what's kind of fun about it is just showing that computation on symbolic objects is such a broad conceptual thing. I'm usually more interested when I have clients who have their own new domain, and then we take these kind of ideas and say, how do we represent your work symbolically so that we can automate computation on your worldview? So now would be a great time, if you haven't already, to put some questions into the chat, and I will take those in just a moment. Let me just sum up here then what the headlines are. If you haven't forgotten, a quarter ago, AI assistance for everyone, out of the box and more conveniently accessible so that you can help you write code and get your computations done faster with, and actually the model that is free we've also upgraded the model. So the free model that comes with every subscription is actually a slightly better AI model than the paid model was in version 14.3. And if you are paying for model, you're getting an even better model at version 15. So all the models have been upgraded to make its code writing smarter, as well as the tooling being better to join it in. Notebooks faster and a little bit prettier. Data, multi-value time series, the new model fitting framework, and general performance improvements across data. Language is all really mainly about making production quality code easier to write and large scale code easier to write. And then we've got things in all kinds of different areas, depending on your interest, that have touched different bits of core maths and these sort of more specialist narrow areas. So I give you Wolfram Language version 15. I think it's an exciting release. the biggest we've had in a few years, and available, of course, on the cloud right now, and to all of you with active licenses for download immediately. And I'm going to turn here now to see the questions.
We've had just an amazing an amazing collection of questions, and we've pretty much stayed on top of them, John. So I think I mean, go ahead and take a look, and you might want to take a look at publish too. It's just some really great information in there. Like I'm going to share this one, asking about previous versions and if notebooks are still compatible. And the answer is generally yes. And as Arden points out, there could be edge cases, but it is just amazing that notebooks from 1988 will open and run in version 15.
Yes, I have seen the incompatibilities list, and it is really super obscure. So the things that we've deliberately changed are, you know, they're kind of sub properties of some algorithm that we've had to tweak, and there's only a handful of them. So anything that is a problem is more likely to be a bug, which of course is always possible that we've accidentally broken something. Of course, when you change things like bsolve now is much more likely to give a more compact differential equation answer than it did before. So those are better, but of course they are different. So if you relied on it coming back with some convoluted 20-term expression and you're taking out the 18th term and now it comes back as a 4-term answer, then, you know, that can cause problems. But I don't consider those incompatibilities. They're improvements that somebody's workflow will rely on it doing the bad thing always. Okay, first question on my list here is version 15 spent 5 minutes downloading GPU SDK. Yes, so this is true. When you use the GPU array for the first time, it will fetch a bunch of libraries that can be significant, but once they're downloaded, they're cached on your machine, and they're different depending on I think who you are. If you're a Mac user, then you have different GPUs going on than the Windows user with CUDA. So there's a whole bunch of different libraries that are needed to support the hardware, but that is a first time use only. So if you're wanting to make use of those things, just do a test calculation once before you're in front of a big audience, and they should work. There are some ways to interrogate what the GPU code is using, but they're all undocumented. If we could take that as a question, we can get somebody from the kernel team to follow up on what the undocumented functions are for querying what goes on behind GPU array. And you know, the coverage of course varies. That if you are using a modern powerful GPU would get much better performance than I did. You know, you don't have any choice on the Mac, but equally if you've got a very old GPU, it may not be supported or may be poorly supported. So performance benefits will vary depending on your exact GPU that you've got in that functionality.
There's been a couple questions too, diving into some of the specific functionality, the mathematical computation functionality, visualization, and so forth. So just a reminder to everyone that we will have the developers on hand and presenting and answering questions at our follow-on webinars that follow over the next 4 weeks. So please review that list, and that would be a great opportunity to interact and ask your questions and make your suggestions directly to those developers in those sessions.
Okay, so Anton asked new developments for Wolfram symbolic transfer protocol. I'm sure there was a few bug fixes and general maintenance, but there was no significant feature that's on the list for WSTP. Is there an option where I don't automatically install version 15? Yes, at the moment, actually, we do not support automatic updates. So you must choose to upgrade to version 15. So we will not be pushing for it on top of you if you're a 14.3 user and you're not ready to upgrade. The same is not true of the cloud. Of course, the public cloud, we upgrade the whole thing because it's all synchronized on the current version. But if you are using a private cloud, again, you can continue to run on 14.3, and I think we haven't actually shipped private cloud 15 yet, but when it is available, it'll be at your discretion when you upgrade. So does the chat, the AI assistant, have a project environment where you can teach context of work it's helping with this? The short answer is no, not right now, but there is a significant bit of work going on in AI skills, and my hope is that those will be Packlet updated in the field. So when those things come online, they will just be, those will auto update if you're on version 15. And certainly when you're using the plugins for developer tools, if you're using things like Claude Code, then I've certainly had success in using skills within those that are Wolfram language oriented skills that say, if I ask you to do this, I mean use the Wolfram language and use the MCP server or use Wolfram scripts to execute and things like that. I'm afraid I don't know the answer on whether we're going to be supporting Intel NPUs. I suspect it's in the class of wait and see, that when they're popular, we have always done a reasonably good job of picking up support for hardware once it gets traction, but it may be a bit early for us to jump in on that one at this point. So, but it certainly is not in the immediate list that I have been seeing. Oh, I'm doing poorly here on questions I don't know the answer to. Question about object management group system modeling language API supports. I'm afraid we're going to have to run that one by the system modeling team. I'm a Wolfram language expert, not on the system modeler side of things.
Yeah, we left the more obscure ones for you, John. But thank you so much. What a fantastic presentation.
So somebody asking what's the difference between the free assistant and the higher pro level. So there are three choices. There is the free assistant, and there is a pro subscription. The difference is the model that it's being used. So we're using sort of more frontier models that are smarter and a bit more expensive for us to run for the pro subscription. So the tooling's the same, and there's no deliberate significant difference in the quantity of tokens that are available to you. Both are intended to be enough for regular data year use for normal users. There is a third tier which is called research, and that is the pro tier but with a lot of tokens. So if you are doing programmatic LLM work, then I mean, you can use the free and the pro for programmatic LLM work using functions like LLM synthesize, but it's very easy to scale demand with those by writing a loop that will go around and ask 1 million AI questions. And the number of tokens included in the free and pro account are not intended for that kind of scaled use. The research tier is intended to scale to very large numbers of tokens. So that's the difference between the pro and the research. Same models as pro, but with tokens intended for more than just coding assistance use, intended for scaled programmatic use.
I put a link to the AI access information in the chat, so you can check that link out.
Yeah, and it looks like Paul's question's being answered by Luke, so I won't take that one. So I think, did you say there's some in the chat you want me to look at?
No, we're good.
Okay, so I'm out of questions that are in the queue. No, there's already one. If I have pro access already to GPT 5.5 Pro, can I use that subscription to access? So yes, you can instead of using the Wolfram model as your default model, or even on a specific model, you can set the LLM evaluator to any API key for any third-party AI that you have. And that is now better than it was in 14.3 because you can make use of the tooling because there are the APIs to be able to feed in things like documentation lookup to make it better at writing Wolfram language code. So yes, that stuff works seamlessly as well. Can I write code in the new package format in version 14.3? So I think the answer is, strictly speaking, no. But it might work because we've actually been using the new package format internally for a while as we've been refining the design of it. And so unless we change the names at the last minute, it may well work by accident because it was an undocumented feature in 14.3. But I wouldn't trust it, and it's certainly not guaranteed. So if you're writing packages that you need to be able to share with 14.3 users, then continue to use the begin package format for a bit longer. In a year's time, the number of 14.3 users, judging by previous history, collapses pretty fast. But in the short term, your packages you should assume, are not backwards compatible if you use the new package format. Like any new function, if you use anything that's new in 15 and run it on 14.3, it'll say function not recognized. It'll just be an inert symbol in previous versions. Do you support local AI models on Mac systems? We do support local AI models. You can use Service Connect to connect to various models. I cannot tell you off the top of my head what the range is. I have done it myself with I forget what the kind of really popular modest size model is that runs on a small Mac. But yes, you can do that. You have to use Service Connect to set up the connection, but it's relatively straightforward. I think there's some discussion on the Wolfram community about doing that if you search for that. Are any of the popular elements better at working with Wolfram language than others? I'm going to point you to something here. Give me a second here to get this a browser on screen. If you Google Wolfram LLM benchmark, we maintain our own self-serving benchmark of. Oh, have we taken this down?
I think there's an issue with rendering in Chromium-based browsers. I couldn't tell you why that is, but it was the same issue that's affecting
to Firefox on here. Okay, well, go here, and if there's a if it's because I'm using Chrome, I apologize, but this is supposed to display, unless this is just simply gone wrong and I just need to do a refresh. We maintain a grid of models and 2 columns of hallucination of syntax accuracy and hallucination of function names accuracy. And you can see who's on the leaderboard of that and what the percentages are. When you add in the reading documentation on demand, all models can be improved by feeding them that as part of the prompt. But these numbers are the out of the box, just using the LLM and asking it to write Wolfram language code. So yes, open that in a browser that works. If we don't already have a bug in on that, we should get that fixed. Will AI Assistant be available to Wolfram Engine 15? No. Well, yes and no. The free subscription is with Mathematica licenses and Wolfram 1 licenses. It is not included with and it also included with trial licenses of those products, but it is not included automatically with Wolfram Engine. But it can be made to work with it. So if you're making a Wolfram Engine powered application and you want to have Wolfram LLM behind it, then just like any application that you're building using Wolfram Engine, you should talk to somebody in business development or on the Wolfram Engine team about the best way to do that. So technically it can work, but it is not part of my, it's available to all users everywhere claim at the beginning of this talk. So with those with API connections, will those connectors connect to projects in ChatGPT or Claude? Yeah. So if you're using, there's two ways to answer this. There is, if you're using Wolfram as your interface and you have API keys for those things, then you can call your API keys to things like ChatGPT or Claude as the back end. But also, if you're using things like ChatGPT desktop or Claude desktop or Claude code on the command line, then the AI tools that I showed you at the beginning that you can install, you would install the Claude code or the Claude desktop tools, and that would make your local MCP server and other tooling that's Wolfram language specific available to your Claude desktop or your Claude command line, Claude code setup, so that it could run Wolfram language code and call on the tools as necessary. And if you are using something like Claude desktop and you don't have Mathematica tool, there is the public MCP server that you can also declare to Claude Desktop, and then it will call our free public server. But that's really casual, light computations like you might use Wolfram Alpha for. It's not really the way you would do developer level stuff. Yeah, so if you're using Pro in Research, how are we supposed to teach concept? Okay, so it is principally in the prompt. The other thing that you can do at the moment is that you can create your own persona for chat notebooks. And if you look at, I think I've got a recorded webinar somewhere on how to build a persona, because you can now use the Wolfram AI as the backend on the persona. You can get all the benefits of the Wolfram Notebook Assistant, the Wolfram AI Assistant, but with pre-prompting built in. So you could set up your own AI persona that you call My Persona, and it has the pre-prompting baked in. When we have proper support for tools and these sort of environment files, then that stuff will be more convenient. And it is being worked on, but it's not on this release to have environment type capabilities. So I think this is Jamie telling me that it's time for us to wrap up. So do fill in the survey to give us feedback on what you'd like. And do remember that in a week, you will hear from the developers themselves, initially talking about the dataset and time series. And I encourage you to come back and hear the deep dive on those areas of functionality. Thank you very much. And I hope you enjoy Mathematica 15.
Hope to see everyone next week. Thank you, John.